What if I told you that life's biggest mistakes might actually be its greatest triumphs? Today we're diving into a really cool paradox in biology, how imperfection, those random little errors in our own genetic code, can actually be the secret key to survival.
So, let's just jump right in with the big question. How on earth can a genetic mistake, one that causes a really serious disease, also be a lifesaver for millions of people? It sounds totally backward, right? But you're about to see that nature is just full of these wild trade-offs.
And yeah, that's what we're going to frame our whole story around, this idea of a perfect flaw. It's a concept that really makes you rethink what's good or bad when it comes to evolution. But okay, before we can solve this paradox, we've got to get the basics down. We need to understand how life's instruction manual is written, and how sometimes it gets typos.
First things first, the gene. The easiest way to think about a gene is as a single recipe in this massive cookbook that is your DNA. It's just a specific section of DNA that holds the instructions for building one protein. And proteins, man, they do pretty much everything in our bodies.
So what happens when that recipe gets changed, even a little bit? Well, that's a mutation. It's a spontaneous change in the genetic code. And it's not automatically good or bad. It's just a change. This process is absolutely critical because it's the only way new versions of a gene ever get created in the first place.
Let's really hammer this home with a simple metaphor. Imagine life's entire genetic code is this enormous, complicated instruction manual. A mutation is like a single typo. Now, sometimes a typo doesn't change the meaning. Sometimes it turns a sentence into nonsense, and sometimes, incredibly, it creates a brand new meaning, an unexpected advantage.
And that brings us to our perfect case study, the one that illustrates this whole idea beautifully. We're going to look at the sickle cell gene, a single typo with some truly dramatic consequences.
So what exactly is sickle cell anemia? It's a genetic condition, and it all comes down to a protein called hemoglobin. Hemoglobin is the superstar inside your red blood cells. Its job is to grab oxygen from your lungs and carry it to every other part of your body. This mutation messes with the recipe for that exact protein.
And wow, the visual difference is pretty stark. On the left, you've got your healthy, disc-shaped red blood cell. It's smooth, it's flexible, it's perfect for squeezing through tiny blood vessels. But on the right, that's a sickle cell. That one little typo in the hemoglobin gene causes the cell to warp into this crescent C shape, especially when oxygen is low. These sickled cells just aren't good at carrying oxygen, and they can cause all sorts of problems, like clogging up blood vessels.
Which brings us right back to that nagging question. If this mutation causes all these health issues, why is it still around? Why is it actually common in some parts of the world? Shouldn't evolution and natural selection have just gotten rid of it by now?
And here is the twist. The answer has absolutely nothing to do with carrying oxygen, and everything to do with a completely different threat: malaria. Malaria is this devastating disease spread by mosquitoes, and it turns out the parasite that causes it has a really tough time surviving and reproducing inside these sickle-shaped red blood cells.
Okay, this table really lays it all out. Let's walk through it. If you inherit 2 copies of the normal gene, great, no sickle cell, but you're a sitting duck for malaria. If you get 2 copies of the sickle cell gene, you get the full-blown severe disease. But, and this is the key, if you get one of each, you're what's called a carrier. You have just enough normal cells to stay healthy, but also enough sickled cells to give you powerful resistance to malaria. In places where malaria is a constant threat, this is a massive, life-saving advantage.
So, you see, it's not a bad gene. It's a classic evolutionary trade-off. Whether it's harmful or helpful depends completely on the environment you're in. If you're in a place with no malaria, the advantage completely disappears. It's a perfect example of how in evolution, context is absolutely everything.
And this isn't just some quirky story about humans. This whole dynamic of a flaw turning into an advantage, it's a fundamental principle of life. We see this same kind of battle playing out constantly on a microscopic scale, all around us and even inside us.
So let's shift gears from our own cells to bacteria. We are in a never-ending arms race with them. For a while, it seemed like we had the ultimate weapon, antibiotics. But bacteria, just like every other living thing, evolve.
I mean, just look at how fast this all happened. Penicillin was discovered in 1928, a total game changer. By the 40s, it's saving millions of lives. But it only took a decade or so before the first resistant bacteria started popping up. Why? Because of random mutations. A few lucky bacteria had a typo in their genetic code that just happened to make them immune to our drugs.
You see the parallel? It's the exact same principle as sickle cell. The environment for the bacteria suddenly changed when we flooded it with antibiotics. A mutation that was probably random, maybe even useless before, suddenly became a superpower. It gave that bacterium an incredible survival advantage, and it passed that trait on.
So, let's pull all these threads together. We've seen how a flaw can save you from malaria, and how another flaw can save bacteria from our best medicines. It's time to really step back and reframe how we think about imperfection itself.
The big takeaway is that these so-called mistakes, these mutations, are the ultimate source of something absolutely essential for life: genetic variation. Without all these typos, every single organism in a species would be a perfect clone, making them incredibly vulnerable. One new disease could wipe them all out.
And this variation is the raw material that natural selection needs to work. It's the toolbox. It provides the options that allow a population to adapt when things get tough, whether that's a new disease, a change in climate, or a new drug. Variation isn't a bug in the system. It's the engine that powers all of evolution.
Which brings us to this final, really powerful idea. Imperfection, variation, all those random typos in the code, they are not flaws to be fixed. They are the system. It's what makes life resilient, creative, and ultimately unstoppable.
And that leaves us with one last question to chew on. If survival so often depends on having the right flaw at the right time, then what does it really mean to be evolutionarily fit? Maybe it's not about being perfect at all. Maybe it's about being part of a population that is perfectly and beautifully imperfect.